So this is lecture 5. We are going to dig into chapter 3 today. So this is Boyle chapter 3. And we've finished looking at solar thermal. So I think we know a fair amount about sunlight. We know that the solar constant is about 100 watts per square meter. We've looked at various solar thermal technologies, daylighting, that good stuff. And now it's time to look at how we take radiation from the heat radiation from the sun and not turn it into heat, rather take radiation from the sun and turn it directly into electricity. So that's really what this chapter is about. So there's a few good things on the physics we need to understand first. So let's just take a look at that. Oh, and I'll come back here and look at this summary one a little bit later too. But let's just get right into the chapter. Unless there's any other logistics questions you guys have, anything at all? Okay. Good. And this is a fairly long chapter, at least in terms of figures. It's got a couple parts to it. Maybe not quite as long as chapter 2, but long nonetheless. All right, so it starts off with a little introduction. I think probably most of us know that photovoltaic panels are made from silicon. I always like when I hear the name of some element. I like to go right to the periodic table, and I like this dynamic periodic table. Silicon, if I remember correctly, sits right here under carbon. It's got, if you look at its orbitals, and I tend to try to think about these atoms geometrically. It's got those it's got 4 openings in its 3p shell, which means it's going to have 4 neighbors next to it. And in general, and this is what's mentioned, the vast majority of that PV cell is just pure silicon. And we'll get into the two doping strategies and exactly what they're used for. You'll also notice that germanium is down here, right beneath silicon. Germanium is also a material used in photovoltaics. It's rarer. I mean, silicon is essentially just sand, and it's mentioned right here in the beginning of the book that it's one of the most abundant, if not the most, or second most abundant element of the Earth's crust. And the other difference between making electricity with a photovoltaic versus making it with conventional steam generation is there's no moving parts. It's all based on how light interacts with matter. So, as it says here, they could in principle, if not in practice, operate for an indefinite period without wearing out. That's barring physical damage, some oxygen getting in, some other kind of impurities getting in. But they're just atoms and they don't break, The configuration that they're in can get disrupted, but the silicon atoms themselves will not break. All right, so that's more or less 3.1. 3.2, a brief history of PV. So photos is light, and volt is obviously just voltage for potential difference or charge difference in a circuit, named after Volterra, who invented the battery. And so photovoltaics, I usually say PV or photovoltaics. A lot of times you'll hear folks say a solar system. I think it's something entirely different when I hear the word solar system, but sometimes you'll hear someone saying a solar panel, but I like to call them PV panels to distinguish them from a solar thermal panel. It's also mentioned right here, the photovoltaic effect, generally credited to French physicist Edmond Becquerel. Here's, there he is in all his glory. Nothing exciting about him. Normally there's some kind of tragic story, but I guess he just kind of had a normal, boring life. Discovered it. From the way I understand it, this thing was discovered more or less by accident, where a material was left in some kind of apparatus and more voltage was present than you might otherwise expect. You sort of, testing these early conduction experiments and just having the lights on in the room affected the outputs of the experiment. So he's paying attention, wanted to figure it out, dug in, and there you have it. So this guy, 1884, first patent application for a solar cell. This comes, roughly 50 years after Becquerel. Edgar Fritz in New York, a selenium cell. Let's take a look at selenium. It's sitting right over here. You can also see its structure is similar. Part of its 4p orbital is full. Its 3d is full, but it's got those two open electrons, two open electron orbitals in the 4p. I don't know exactly what its bonding looks like, but I think what you can at least see from this photo is that he has individual detectors, and then coming off, you have an insulator here on the bottom, and then coming off are the conductors that allow the electrons to flow out of the cell. You can also see that this early system like this, less than 1% of the energy was converted, so not very efficient. Max Planck is also mentioned. I think we talked a little bit about the Stefan-Boltzmann equation last time. It was Planck who actually proposed that energy is quantized rather than being continuous. It was Planck that actually is the Planck constant, and we'll get to that here in a little bit, measured in the joule second is the way to get between how much energy is in a photon and how much energy it's going to generate when it interacts with matter. And it's actually a discrete amount. Semiconductors are mentioned. Here's germanium, as I just mentioned. And the meaning behind semiconductor means it's not a metal. Electrons do not flow quickly through it. And it's not an insulator like rubber. It's somewhere in between. That's all that is meant by a semiconductor. Okay. But the next big breakthrough, and this is Bell Labs, 1948. There's a little shot of these guys working in their lab, is when some impurities were introduced into the material. Obviously, this was called doping, and we'll discuss exactly why that works. 1950s, the efficiency comes up to 6%. Obviously, this is in the lab, and these guys are probably being paid a fairly good salary by Bell Labs. And if you were to sort of look at the dollar per watt value, it would be extraordinary. Millions of dollars per watt, because they're just generating a few little micro. So if you tracked PV technology, we're sitting right now at something like 60 cents a watt for commercial PV. you go back and trace it far enough, this is millions of dollars per watt back in the 50s, so it's interesting to see how that trend has come down. Spacecraft are mentioned. There's better access to sunlight, obviously, once you get outside the atmosphere, so if you can successfully get a PV panel into outer space without cracking, you've got free and relatively unlimited sunlight, as long as this thing isn't back in the shadow of the Earth for too long. You get good access to energy. You can see now, if we look at box 3.1, there's a little measure talking about the best efficiencies are about 25%, and we'll talk a little bit more about box 3.1 and exactly what the standard conditions are. That's going to be something you're going to want to know for the exams. All right, so there's one example. Here's another one, and you can bet that NASA's got access to the best PV arrays. So 130 kilowatts, not too bad. That's enough juice to run 130 U.S. homes, and I don't know that much about the space station in terms of its propulsion systems. How it's using, what it's actually using for thrust. Obviously, with that much electricity, you can run electric motors all day long, pumps, chillers, other instruments that require, focusing telescopes, things of that nature, mostly actuation. And I don't know much about if you'd use it for propulsion anyway, though. I can't think of some way. Typically in space, the only way to do propulsion is by ejecting some mass, in the direction you don't want to go. But anyway, 130 kilowatts, pretty substantial to run whatever systems are there on board. And I don't know that much either about how the HVAC works on one of these guys, but I would imagine it's used for a lot of just pumping and filtering and things like that. You'd think if you set the thing up right, you'd have really good access to some passive solar. Obviously, you're right up there. There's no clouds to get in your way, so as long as you're dialing that in properly, there's probably plenty of heat coming into this. Certainly, there are some insulation issues at just a few Kelvin in outer space that have to be dealt with. But so maybe some of it's used for auxiliary heating as well. All right, so here's kind of one of your exponential graphs, if you will, of total global installed capacity, and this is in megawatts. And so there we're looking at 40 gigawatts basically, and I want to do a quick calculation and see just from this figure what fraction of total global primary energy comes from solar, right? So let's just do that really quick. So then we'll do it as a fraction. So what did I say? 40 gigawatts divided by 16 terawatts, right? So let's run that on the calculator. So 40 divided by 16. So 2.5, yeah, 2.5, and then we got to run the scientific bit. 2.5, and then we're looking at 10 to the 9th, 10 to the 12th, so equals 2.5 times 10 to the minus 3 equals 0.0025. Did I do that right? Equals, yeah, I think I did. 2.5, 10 to the 9th, 10 to the 12th, 2.5, 10 to the third. So that's 1/4%. I think it's much greater than that by now. I mean, I think it's like all the way up to a whopping 1%. We're looking at 2010 numbers, but in 2010, a mere 1/4% is from solar. But if you look at that number, I mean, look at that that plot. Watch this thing take off. And I wouldn't be surprised if that's doubled or tripled by now. Does that make sense what I just did, those little numbers? Because we know that humanity's running at 16 terawatts and solar's at 40 gigawatts. All right. All right. Now, here's the price. I mentioned this just briefly a second ago. So I really do not know why the countries have been anonymized. They don't want keeping secret how much solar they have. But let's just take a look. So there's 6 curves there. We just take the top one, modules. So evolution of price of PV modules and small scale systems in three different countries for, well, about a 10-year period. It says prices per watt are shown in constant US dollars. And systems. It's not really clear to me looking at this thing. Oh, so the dashed lines are going to have to be dollars per watt of the module. Okay. And then the solid lines are basically what it is to have the thing installed. Does that make sense? Yeah. So 2009, they're still at $2 a watt. I just mentioned now in 2015 we're at 61 cents a watt. But at that time you can see that in 2009 they're basically as low as they'd ever been in any of those 3 countries. You can also see that the installation price was basically as low as it had ever been, and that's due to a variety of factors. A lot of it is permitting. A lot of it is market competition. So the more PV installation companies are out there, the cheaper that's going to get. Some of it is racking technology that continues to advance all the time. So there's a variety of factors that play into that. I guess one thing that's kind of interesting to me is the orange line. If in fact the 2 orange lines are the same country, it's intriguing that the installation cost would be as low as it is, even though the cost of the modules was as high as it is. So just something to keep in mind. There's 2 separate there's the hardware, the materials cost, and then the installation cost. And certainly the lower that gets, the more and more competitive it becomes with any other energy system, whether it's renewable or non-renewable. Any power plant is going to sort of have a dollar per watt installation price. And that's usually the best way to think about it. Everyone's, well, how much does it cost? Give them a number in dollars per watt. I was just down at the Roots Fest. A couple gals came up and said, well, how much does one of these cost? And I explained, well, they're now at about $1 per watt. And I'm like, well, what's a watt? And so then I got into that 1,000 watts per square meter. I said, oh, well, here's a square meter. Here's 1,000th of that. So just imagine, putting your little dollar bill in more or less a square inch. So you can imagine, you know, pasting dollar bill, and it ends up being about $1 per square inch on your roof. And it's not a heck of a lot of money. I mean, it's feasible, it's measurable, it's you know, it's tangible. So that's kind of a way that I typically describe it to someone who's not familiar with these units. So you might want to take that with you. Okay, so there's some of the pricing. Now, we did a little bit of trig. Yeah, we did some pretty good trig last week, if I recall. We looked at how much sunlight would come in at 45 degrees, right? We came up with square root of 2.7, so it was better than half. And so here's another picture similar to the one that I ran last time. And the number to keep in mind here is this air mass 1.5. And what does that mean? Well, in this particular diagram, it means that between point O and point S, there's about twice as much air as there is between point O and point Z. And let's look at this air mass 1 over cos theta. And I'm just going to run that for that 45-degree angle we did last time. So let's do that. Let's do that. Air mass equals 1 over cos theta. Now, let's just say theta equals 45 degrees. If you remember from last time, the cosine of theta and the sine of theta are exactly the same. That's when they crisscross. All right, so let's do this. So I'm going to do, oops, I don't want that smaller, I want that bigger. So here's 45 degrees. Hello, DEG. 45. And here's radians. Equals, so I'm just going to take the function radians. Oops. So I'll start with equals radians of that number. Oh, another thing you might want to try here is if you put in the letter Q and then come over here and highlight it and select symbol, that'll give you your theta. In most Microsoft software, the symbol will give you the Greek equivalent, and for whatever reason, Q is the same as theta. So I'm going to give you theta in degrees, and then I'll give you theta in radians. Okay, and now I'll give you 1 over cosine Q. So, well, first, let's just take baby steps. Insert, so a lot of times you get too ahead of yourself, you get a great big fat formula going in Excel, and you don't know where the error is. So let's just make sure each step is correct. So let's copy that, paste it there, fine, go in here, take that out, cosine theta equals cosine of that number. That's that 70% I just talked about a second ago. Now equals 1 over that number. Okay, so it's almost 1.5. Is what we're looking here in the book is an air mass of 1.5. what's that telling me? If I go back, so is theta and an air mass of 1.5 greater than or less than 45 degrees?
The air mass is greater.
The air mass would be greater, yeah, and so that theta would be actually more open.
Yeah.
Right, because what we're to make this number bigger, that would have to be smaller, and as cosine gets closer to 90 degrees, it also gets smaller. So I'm just kind of thinking out loud here a little bit about where the sun spends the majority of its time. And in general, the sun is never like directly overhead, and most people don't live at the equator. So assuming an air mass of 1.5 rather than this 1.4 that we looked at is probably closer to a global average. So that's where that 1.5 comes from. All right. Another thing to keep in mind, I'm looking at that 1365 watts. That's another thing. So 1365 watts per meter squared. That's at an air mass 0. And 1,000 watts per meter squared is an air mass of 1. Now, we can check those two numbers too. Let's just do that really quick. Well, and you can see that those don't agree exactly either. If they did, this number would be 1.365, right? So it's not a perfect science, but that's the definition. So an air mass of 1.5 is the global standard, and that's just defined as 25 degrees Celsius and 100 watts per square meter. Okay, there we go. All right. Yeah, there we go. Cosine of so that would be a cosine of 48 degrees. It says they're right on the second page of that book, or that box. All right. Okay, so that's this guy. Yeah, this figure is always a little bit, a tiny bit off-putting to me. I guess this this green line is the theoretical black-body radiation from the Stefan-Boltzmann equation. This is what the sun is actually doing. So if we read here, it says the spectral power distribution of solar radiation corresponding to air mass 0, and obviously down here, air mass 1.5, where a lot of the light is attenuated. It says the green was if the sun were a perfect radiator or a perfect black body at 6,000 degrees Celsius. Well, no such thing as perfection, but that's what the theory would hold. All right, and then so it's basically this stuff at the bottom that we get to harvest after the atmosphere has had its way with it. All right, let's take a quick break there.